So, today I am going to talk to you a little bit on the concepts of modern catalysis and green chemistry, mostly on modern concepts of modern catalysis. So, I start with what happened several centuries ago, how the catalysis started. Catalysis was initially recognized in 1816 by Davy. This is in a mine safety lamp. Some of you may know that, right? Then Berzelius in 1835, 1836, he defined this, what is catalysis. Ostwald connected this to chemical equilibrium of a reaction. That is a timeline of the catalysis topic, catalysis research or catalysis area has been developing. Then there is empirical systematic experiments were done by Mitash, because they had to do some empirical experiments to establish the concept of catalysis or the action of catalysis. So that has been going on in 20th century. Okay, and then somewhere in mid 1920s, Langmuir and Hinchelwood started talking about the kinetics of this catalysis, particularly heterogeneous catalysis. Homogeneous catalysis is there, heterogeneous catalysis they started looking at how do we actually measure the kinetics. Can we do some experiments and measure the kinetics and then predict the reaction rate and so on and so forth. That is what they were actually looking at in 1920s. Then kinetic analysis of kinetic process carried out decades after that, several decades, almost 1920 to 1960, that 30-40 years, people have been working on that, looking at how catalytic action is taking place, how rates are changing, what are the factors that affect the rates, so on and so forth. Somewhere in 1950s, they started synthesizing other kinds of catalysts. For example, zeolites are very popular, zeolites, and now there are many other porous materials. Application of spectroscopy and microscopy techniques started somewhere around 1960 or 1954. Till 1954, there was no serious spectroscopic technique which can actually probe the catalyst and tell us that what is there on the surface, what is going on the surface. So, somewhere around 1954, that is the beginning of the catalyst characterization using FTIR, spectroscopy, particularly CO adsorption on copper. That was the first time spectroscopy technique was applied to understand catalysis. Spectroscopy is important. Today, without spectroscopy, you can't do anything. You have to have spectroscopy to understand what is going on in molecules, atoms, materials, compounds, the structures, and you need to analyze all of them. Right? Spectroscopy, microscopy are very important. So that kind of an analysis started only in 1954 and after that. Okay. Now, then what happened, the surface chemistry and spectroscopy techniques started coming up, particularly catalysis is nothing but some reactants have to adsorb on the surface and undergo transformation and then produce products, and then the products have to dissolve. So, you need to understand this entire all these steps to get the mechanism to understand the reaction rates. So, that is where surface chemistry and spectroscopy, surface spectroscopy techniques started coming in, and this is around somewhere around 1960s, 1970s these things started coming, and then but they were applying to single crystal surfaces, because polycrystalline surface is very difficult to define polycrystalline surfaces. Single crystal surfaces you can define. How will you define single crystal surfaces? For example, all of you know different planes in the crystal, 100 plane. You are all aware of that, right? So, can we have a crystal which can be cut in 100 plane and see how atoms are arranged on that? Right. So, if I have a large crystal of button size, so I know the atoms how they are arranged if it is oriented in 100 plane. Then I can study that, it is very precise. So those things have been done using what is called surface science approach, that is 1970s. ETL has started looking at this, and ETL and there are many other labs around, even Indian Institute of Science, they started looking at these problems, and then ETL got Nobel Prize in 2007 by carrying out this one, these studies. So, the reason why people do these surface studies, surface science studies, is to understand what are the intermediates formed on the surface, okay, and then how molecules are intermediate species are transforming from reactants to products in between intermediates. So, that helped to understand the little more about the catalytic science, rather than it was earlier people call it as a black magic, but it is not known a black magic. There are a lot of understanding has happened because of the surface science approach to catalysis. Then somewhere around 1982, around that time, scanning tunneling microscopy was invented. Scanning tunneling microscope, how many of you are aware of scanning tunneling microscope? Normal microscopes, optical microscopes, right? And then scanning TEM, transmission electron microscope, right? Scanning electron microscope, but this one is scanning tunneling microscope, right? So, this one is developed in somewhere around 1982, around that time. Then the people started using that the microscopy to understand what is going on surfaces. So, the principle of that is there will be a cantilever which will go and then which will touch the surface, and then you scan around the surface. Then there is a small current which passes through between the cantilever and the surface. That current is expanded to surface image. Okay. So, that has actually improved the understanding of the surface structure and surface species with atomic precision. You can actually literally look at each atom using scanning tunneling microscope. Okay. And then around that time, ammonia synthesis catalyst, that Haber process all of us know, right? It produces tons of ammonia which we all need it. But then nobody understood the mechanism of this ammonia synthesis on iron catalyst. Iron catalyst is a combination of iron oxide, iron, aluminum oxide, potassium, so many components, it's a mixture of, it's a very complex material, but under the reaction conditions at high temperature and high pressures, it works beautifully. Till now, we have ammonia synthesis reactors based on that, but no one understood what actually is how exactly nitrogen is converted to ammonia, because nitrogen and hydrogen is coming and then reacting on the surface of iron. If there is no catalyst, nitrogen and hydrogen, if you want to get ammonia, it is not so easy, right? So, that has been studied very extensively by ETL, and so that is the reason why he was facing he actually produced a energy profile of ammonia synthesis. What he could do is he could actually predict if I have a catalyst like this, the rate of the reaction is going to be this much. So, he could predict that. That is not an easy task to do it, but of course, that is one of the things. He did many other things, that for that he is recognized, got a Nobel Prize in 2007. Then around that time, Fischer-Tropsch synthesis of alkanes in 1990, Fischer-Tropsch synthesis of alkanes was also a very popular thing that had happened, particularly using iron catalyst. And then around somewhere in 1992, instead of iron, people started using non-iron ammonia synthesis catalyst in 1992. Around that time, that is non-iron is ruthenium. Ruthenium is also used as a catalyst. Now, when you actually make a material, you have to know what that material is. Suppose you have a powder, some powder you have. What is that powder? right? You can make a lot of powders, right? You can see variety of powders. What is that powder? How do you analyze that? You need to have techniques such as XRD. XRD, how many of you know the XRD, X-ray diffraction? That is a Bragg equation. That is a simple way of identifying the phases present in the catalyst. Suppose you have A, B, C, D phases present in the single mixture, you can identify them. So, catalysts contain variety of phases sometimes. So, you have to use XRD. You cannot, there are other techniques also like FTIR. FTIR is basically to study adsorbed species because there are vibrations. The adsorbed species vibrate. So, you can identify the vibrations of the adsorbed species, right. How many of you are aware of the IR spectroscopy topic? Okay. So, IR spectroscopy is a very powerful technique. Actually, people started only with IR spectrum, later on only all the other techniques came. IR was the readily available and people started using that. And then of course, there is other techniques here. These are all Raman spectroscopy was also there. Now X-ray photoelectron spectroscopy, Oj electron spectroscopy, so on, so forth. There are so many other techniques are available now. Okay. So there are 3 steps here. One is synthesis of a catalyst with a particular activity, selectivity is a challenge. Once you do that, that requires a lot of chemistry background, chemical knowledge, and then what exactly product you are looking for, that knowledge is important. Once you prepare that, then you have to see what you have prepared is the correct one that you wanted to actually prepare. For that you need to have some of the spectroscopy, microscopy techniques to check whether it is formed properly or not. Once you are convinced, then you use it for doing the reaction. Okay. So, these are certain steps that are involved in this. Apart from that, there are computational studies which can provide geometries, bond strength, and then etc. There are a lot of computational studies, computational techniques have been developed in the recent times. Now, actually, there are many more. They are developed particularly to see. Sometimes you may not be able to observe some certain species on the surface, but you can predict using the computational techniques, or you can also substantiate what you have learnt from your experiments. Okay. So, computational catalysis is also very important, particularly to there are people who are working in the computational catalysis. I mean, who are interested in computational using computers and then to design a catalyst and to understand the catalytic surfaces, the reactivity, species, etc. You can actually use computational methods. There is also combinatorial approaches of catalysts. There is something called combinatorial approach. Here, what they do, they can test, they can actually computationally, they can actually look at several possibilities of catalytic materials and then see which is the best one, rather than working in the lab and synthesizing them and then testing them. It is a long time process. No, computationally you can actually look at different options and then choose one of them, the best one, and then test it in the lab. So those kind of approaches are also there in the currently. That is only essentially to discover new catalysts by saving time. Okay. All these things happened last 200 years. We still have challenges remaining in designing catalysts with good surface reactivity and selectivity. We have understood a lot, but still there is a lot more to understand. There is a lot more to understand. Okay. So, if you see here, this is a timeline. So, this is the William Ostwald, is a Nobel Prize in 1909. He is a person, initially from 1800 to 1900, this 18th century, this is basically 19th century, you see here, not much activity is there. Not much activity is there here, right. From 1900, see this is the time where Davy, Berzelius, all the equilibrium thermodynamics, was picking up, the subject was being developed, and then somewhere around 1900 onwards it started picking up the catalytic, the activity. You see that this line you see, expansion of industrial catalysis. That starting point was ammonia synthesis. Starting point was ammonia synthesis. For that, Haber tested something like 2000 materials, and then finally he figured out one or two, and then iron was the cheapest. So he took iron, and Haber actually developed the required chemical engineering background of that. The technical background was provided by Haber. That is why we call it the Haber process, Haber process. So from there onwards, then they started picking up. See, expansion of industrial catalysis started. Now we have so many industries in India, catalytic industries. For example, HPCL in Bangalore, they have what is called Green R&D Center, HPCL. Some of you can have a look at it, Green R&D. They have lots of facilities, and then they do lot of catalysis related activities there. Advanced catalysis and also the industrial catalysis. They do research, they also do pilot plant studies. Green R&D Center, HPCL Green R&D Center in Bangalore. Okay. Then from here onwards, when it picked up, but then it was just around here, but now there is a lot of, after that there are so many variety of catalytic processes have taken place in industry. For example, ammonia synthesis, hydrogen production, then gasoline, using geolites, etc. There are many more industries, In Chennai, do you know where these industries are located in Chennai? Industries mostly which use a lot of catalysts and then in the chemical processes. You are all from Chennai, no? There is something called, what is that, North Chennai. North Chennai, there is a place, I forget the name of that. There are a lot of industries where you will find these chemical industries there, where they use variety of catalysts for various processes. Okay. And then simultaneously, if you see this dotted line here, Langmuir started defining what is catalysis. Langmuir started defining what is catalysis. That is where do you strike? Does it strike you in your mind what is Langmuir when I say Langmuir? Langmuir isotherm. He started quantifying it, because there was quantification is also important, right? So he started looking at quantification of this phenomenon. That's where he proposed Langmuir isotherm, based on some 3-4 assumptions. Of course, those assumptions were not entirely correct, but nevertheless, under certain conditions, Langmuir isotherm is correct. Okay. So he proposed, Langmuir started looking at it, and then Hinshelwood also stepped into that, and then they both proposed Langmuir-Hinshelwood mechanism. Some of you may have studied that. Langmuir, in physical chemistry textbooks it is there. Langmuir-Hinshelwood mechanism. Those are very important things. So they actually quantify. So one can measure the rates and then try to quantify the catalytic reaction mechanisms. Then comes this transition state. Thermodynamics is important, because catalytic reactions are also thermodynamically controlled, right? What all that catalyst does is to shift the equilibrium towards the product, right? Okay. So transition state theory started picking up. So that also contributed. Then comes somewhere around here, as I mentioned, IR spectroscopy started coming in, where they started looking at catalytic materials, analyzing them by IR spectroscopy. And then comes surface science here, 1970s, surface science, surface spectroscopy, surface science studies started available. So people started looking at the catalytic surfaces, catalytic science, active site, structure, mechanisms, etc. These are all things which people started focusing on. Earlier, going to atomic level was very difficult. There was no way to go at atomic and molecular level. But then once the surface science techniques are available somewhere around 1970, 1980s, then they started looking at active site structure, where exactly the catalytic action is taking place. Why is it taking place? What is the structure of that particular site? Okay. So those details have been now are available now, at least to some extent, to certain materials, certain catalytic materials. Then 2000 onwards, last 2 decades, in situ operando techniques started coming in. This is the one now currently everybody is talking about, in situ operando. Means here these active sites, all these things, you study under certain conditions like vacuum, etc. But what exactly happens is, when you prepare a catalyst and then carry out the reaction, under the reaction conditions, can you actually analyze the material, the catalytic material and the species involved in that under the reaction conditions? That takes you to what is called in situ techniques, operando techniques, the in situ XRD, in situ XFs, in situ IR. So they started using these techniques to get more information about how reactions are going on the surface of the catalyst. So this is a current one. This is a current one. Okay, and these techniques are not only here; these techniques are now used in industries also. If you go to industries, for example, you go to Bombay, Reliance Industries, in Gujarat, they have an R&D center where all these techniques are there. They make catalytic materials and then analyze them in their R&D center, and then get information about, full information about the material, catalyst, and then use it. So industries also started establishing R&D labs where they would like to know this information about all these things here. Okay. So now we are at that level. So earlier it was only a black magic. Now we are actually coming slowly towards looking at the atoms, molecules, species, intermediates. We are able to now, we are at a juncture where we can actually look at them. We can actually identify them. So that is the exciting thing that we have in this area. Okay. So I just show you, this is a Fritz Haber, 1918 Nobel, Karl Bosch in 1931 Nobel, and Irving Langmuir 1932 Nobel. This is the Langmuir. That's why we have a journal called Langmuir. Are you aware of the journal Langmuir? There is a journal called Langmuir for publishing your research findings. Very nice journal. And then that is actually on his name. And then Gerhard Ettel, 2007 Nobel. He is the one who works in Fritz Haber Institute in Berlin. He has many of these in situ techniques. So where are we now? Heterogeneous catalysis, current focus is on structure, activity, actives, spectator surface species, operando spectroscopy, computational methods, selectivity, chiral surfaces, stability and durability. All these have to be looked at. Look at that, there is one interesting thing happened here, chiral surfaces. Now you can actually design catalysts with chirality on the surface. So you can actually, if you have chiral molecules, you can get selectivity one of them. If you have two chiral molecules, you can actually synthesize one of them. Selectivity will be very high. So you can have chiral surface also. Okay. So that is a challenge. Of course, designing the chiral surface is a challenge, but that is what is currently being looked at. Chiral surfaces. This is another interesting area that is picking up. So just to give you, catalyst is formally assumed it remains unchanged during the course of the reaction. That is what we have been taught in the class. And then it involves, of course, in chemical bonding during the reaction. That is catalyst. And catalysis is cyclic process which reactants are bound on one form of the catalyst, and then products are released from another, regenerating the initial state. This is a cycle here. See the cycle here. So this is a catalyst. This is a catalyst, and then the reactant comes and sits on that catalyst reactant, and then reaction takes place here on the surface, and then products come out and catalyst gets released. This is a cycle. This is a cycle. This is what people have been looking at earlier, but now we are not very happy with that. What happens here? What is this? We want to know more about the information about what that is in situ at atomic level, molecular level, what is happening. That is what we are now looking at, we are focusing at currently. Okay. Of course, once you understand this, once you understand this step, you get a lot of information. You can use that information to design catalyst. You can use that information to increase the reaction rate. You can use that information to increase the selectivity. You can use that information to increase the stability of the catalyst, so on and so forth. Okay, all right. So for the industries, what they do, they basically they have a catalyst which is a mixture of substances that increases the rate of the chemical reaction. They just don't know what that. There is a catalyst. There is a material which is a mixture of some substances, and then they use it for the chemical reaction, right? And they want to have which provides alternative and quicker reaction path without modifying thermodynamic factors. Okay. But what happens is, at the end, catalytic process, the catalyst will remain same. But currently there is some understanding, catalyst also gets involved in the catalytic process. It may change a little bit electronically, it may change, right. So that is possibility is there, but basically it should get regenerated, you should be ready to again to go back, pick up the reactant and then give the product. The cycle has to be complete, otherwise industries will not use that, because it is not economically viable. See, if you see catalysts, you have the variety of things. These things some of you must be knowing: heterogeneous catalyst, the homogeneous catalyst, heterogeneous catalyst, heterogenized homogeneous catalyst. Such, for example, biocatalysis, enzyme catalysis, acid-base catalysis, homogeneous further divided into acid-base catalysis, transition metal compounds, heterogeneous catalysis, bulk catalysis, supported catalyst. There are a variety of catalysts are available. There are good books if you want to read these things. So what we are going to focus is, we are going to focus mostly on heterogeneous catalysis, heterogeneous catalysts. What kind of process that can occur on heterogeneous catalytic surfaces? You see that, so this is a heterogeneous catalyst. You are looking at the atomic level. You have atoms here. These are all atoms here. This is a catalytic surface. Okay, and then you have these molecules sitting here. These are all add atoms. So there is a if this is a surface and this one is a vacancy here. This one is a vacancy. This atom is going and sitting here. That is a add atom. And then you see this. There is a step here. And then these are some poisons or adsorbed intermediates, right? And then there can be interaction between this molecule with the surface. Then the electron transfer can take place, right? In all these cases, you see there are so many things happening here. So gas phase reactants come here, they physically adsorb. Then you have a variety of intermediates, adsorbed reactant. There is a charge transfer. And then the molecule can get dissociated adsorption and they diffuse from one place to other place, and then finally they form a product, and this product is the one which is going to come out. So many complex processes are taking place before you get your product. Our forefathers did not know all these things, so they just closed their eyes and then they got a product and they are very happy. But now we are not that, we want to see what is going on inside, right? Because we have the techniques available to see that. So this is a very complex, catalysis is a very complex phenomenon, particularly heterogeneous catalysis is a very complex phenomenon. Now you see, in the industrial catalysis, what they do, basically they worry about these three: activity, selectivity, stability. Doesn't matter what material it is. They have to You have to have a good activity, good selectivity, good stability, then only they will invest money, industries, right. So, catalysis offers a possibility of fast and selective production of the desired chemicals. For example, one of the reasons why we are using catalysis is reaction should be faster, reaction should be selective, right. Now, I have given an example here, reactions of synthesis gas. Synthesis gas, you know, this is CO2, H2, in a certain proportion is called synthetic gas, synthesis gas, very important, synthesis gas, carbon monoxide and H2, not carbon dioxide, carbon monoxide. Take this as a reactant and use variety of catalyst here. Use nickel, you get methane. You use copper, chromium, zinc oxide, you get methanol, that is methanol synthesis. And you use iron, cobalt, then you get hydrocarbons. You get hydrocarbons. Same reactants, catalyst is different, product is different. Okay. So, we have to be very careful what we are choosing. Now, suppose if a rhodium cluster if you use, you get methanol, glycol, you can get glycol also, right. Reactant is same, reactant mixture is same, but you get variety of products depending on the catalyst that you are using. So, you need to understand the properties of the catalyst very well and then design it, okay. Now, here look at this methanol, this is the input methanol, and then where you have this plus carbon monoxide, you use rhodium and iron and then HI as a co-catalyst, you get acetic acid. If you see here, same methanol, you can also get acetaldehyde. If you use zeolites, you get hydrocarbons, and if you use ion exchange resin, you get methyl trimethyl MTBE, and then if you use silver alumina or Fe, iron manganese oxide, with sodium oxide, this material, then you get methyl formate, formaldehyde, etc. You see that? So, catalyst has, each reaction has a specific catalyst which will work, it will not work for any other reaction. And why is it so, is a question. Now, that we need to understand the catalyst characteristics, acidic sites, basic sites, structure of the catalyst, right, and then whether it is stable under those conditions. So, these are things which you need to understand to design a catalyst. Choice of the catalyst, that is where the choice of the catalyst comes into picture. For example, here activity is expressed in terms of rate, of course, that we know that rate is the moles per product per volume of catalyst per hour, or turnover number. Are you aware of turnover number? Turnover number is very difficult number to define, but turnover number, that is mole of product per mole of catalyst of or active site. Per mole of catalyst is okay, but active site means, you know, it is very difficult to find out active site, number of active sites, right. Number of active sites is difficult. So, usually people give in terms of per mole of catalyst. There are methods to find out active site, right. So, but that is not an easy job, but this is the definition. So, higher the activity, higher the productivity, of course. There is selectivity, chemical selectivity, particular product, stereo selectivity, regio selectivity, as I said, chiral surfaces, they can give you stereo and regio selective products, okay. Lifetime is important. If the choice of the catalyst, the people have to look at A, B, which one is, which has a lifetime is very important, and then we can regenerate it. Suppose say you use the catalyst for some time and then you have to regenerate it. If you can't throw it out, you can regenerate it. That factor also comes into picture. Toxicity, some of the catalysts are toxic, you can't inhale. So, toxicity also has to be taken out. Of course, price, money, right. So, these are some of the considerations to choose a catalyst. Once they choose a catalyst, so you have to get the chemistry of the catalyst, right. structure of the catalyst, so on and so forth. So quickly I will give you some example of preparation of catalyst. So people prepare catalyst in various ways. So they take catalyst need to be calcined, fired in order to decompose precursor to receive the desired thermal stability. Effect of calcined temperature and time are shown here. What they do now, they start with some precursors. They start some precursors. You want to get X, Y, Z. So you start with X precursor, Y precursor, Z precursor. Mix them at a particular proportion. You need to see what precursor is that. The precursor also can affect the final catalyst, because the morphology can change. So once you do that precursor, then you mix them in a particular proportion, and then you have to fire it at a particular temperature. You can't fire it the way, whatever way you want. You have to fire it at a particular temperature, so that the catalyst is stable, catalyst is formed. You see here, once you do that, 500 degrees to 700, let us say 900 degrees centigrade, your BET surface area is decreasing. One of the properties of catalyst that is important is BET surface area. Are you aware of BET surface area, Brunner, Emmett, Teller? Right. So BET surface area, normally it has to have very good BET surface area. You take a river sand, what should be the BET surface area? What do you expect? Or not river sand, for example, the sugar crystals in our kitchen. You try to measure surface area, meter square per gram. Per gram using how many meter square it would be? It would be 1 or 2 meter square. But actual catalyst, if you take, the surface area can be as high as few hundreds meter square per gram. The reason for that is, utility is more. When you reduce the size of the catalytic particle, the surface energy is high. So the particle can participate actively in the catalytic reaction. So you need to find out what temperature you have to fire this, so that you get a good surface area, right? And also the time, how many hours you want it to. People use it for 2 hours, 3 hours. If you keep it for longer hours, the catalytic particles, they come and they start centering. They start centering, smaller particle will become bigger and bigger and bigger. Then it loses its surface area, it loses its activity. That one has to take care of that also. Okay, and there are methods of pre-treatments, reduction, sulfidation, activation. Typical catalyst lifespan should be many years or a few minutes. It should be many years. Few minutes will not work. Maybe in the lab it is all right. In certain catalysis, it may be a few minutes, but normal use is activity, it is induction period, normal use and dead. This time should be at least a few years, at least 5 to 6 years. Okay. Now that is the story of how the catalysis developed, and then some industrial ways of looking at it. But then as I said, modern surface science studies of heterogeneous catalysis, people used single crystals to study this. For example, as I mentioned to you, in situ operando spectroscopy, understanding surface chemical processes, structure characterization, structure activity correlation. These are the things which are currently being investigated, and there are a lot of labs in IIT Madras. There are at least, as I know, 6-7 young faculty are actually working in this area in IIT Madras, in chemistry, chemical engineering. So if you see here, let us take an example of ammonia synthesis and see what it is. Time is there, no? Oh, I have to stop, huh? Okay. Okay, so quickly, ammonia synthesis, if you see, the ammonia synthesis has been tested in all these materials. But then it is showing, the best one is ruthenium, osmium and iron here. Sometimes molybdenum also. But iron has already been used. Osmium is not used because osmium is toxic. So they avoided that. Now people started looking at ruthenium also. Okay. Iron is, in the modern studies, why iron is actually active is a question that has been addressed. The reason here is, what people have done is, they have taken this iron 110 crystal, iron 100 crystals and 111 crystals, small crystals, not a regular material, but small crystals oriented in these planes, and then load them in a reactor, small reactor, put some 15-20 crystals and carry out the reaction, ammonia synthesis. And then what people have found is that ammonia production is very high in the case of iron 111 plane. This is possible because of the surface chemistry, surface science techniques. So now in the real catalyst, if you analyze it, you should see more of this iron 111 planes. Small crystallites will be there in the real catalyst. The plane, these crystallites will have a orientation of 111 plane. That is the reason why you get good activity there, right. So based on that, theoretically they try to provide the theoretical basis of that, and then calculate the reaction rates. Even without going to the industry, they can actually predict the rate. If I have this crystal plane, I have this rate, and that has actually matched very well with the industrial production. That is one of the greatest achievements of surface chemistry in the last 3-4 decades. That led to Nobel Prize with Apple. Okay. So people have calculated the ammonia synthesis also by calculations, theoretical calculations. People also have found out that iron, ruthenium, osmium are on the top, and this is the ammonia synthesis on ruthenium. This is a non-iron catalyst. People started using non-iron catalyst somewhere around last 15-20 years. They started using ruthenium also, non-iron catalyst. Okay, I think I do not know whether I have time, but so these are the kind of spectroscopy methods, techniques which are used to study these species on the surfaces. Okay. So I will not bother you, but these spectroscopy signatures show that nitrogen which is sitting here, this is the nitrogen adsorbed on a surface. This is not as quick as, is very slow. Okay. This nitrogen molecule is adsorbed on iron surface, and then it can adsorb in this manner and in this manner, and then this one will break into two pieces, because this is a triple bond, this is double bond. Double bond can be easily broken. So that breaks and then gives you nitrogen atom. This nitrogen atom, if hydrogen atoms are available, they start forming NH, NH2, NH3. Final product will be released. That is the mechanism. And this is aided by adding a promoters called potassium. Potassium supplies electrons, so that the electrons will get pumped into this, and then the triple bond becomes a double bond. Nitrogen has an antibonding orbital. Nitrogen has an antibonding orbital. So you put more electrons in antibonding orbitals. For example, one electron you put it there. What will happen to bond order? So that is what happens here. This is here only one nitrogen is attached to the, here both nitrogens are attached. Suppose if there is a promoter which can pump in electrons into this bond, then triple bond comes to double bond will come to single bond and break. That is a catalytic action. You have that activity like the curve, activation energy. That activation energy is nothing but it is used to break bonds like this, and then form products. Activation energy is nothing but it is invested in breaking some bonds and making some bonds, right. So I just show it now. How many of you know him? At least should know now. Professor C.N.R. Rao. He is in Bangalore. He is 90 years old. He did a lot of this kind of work. This is his lab. Okay. So how do we know? I'll take little more time. How do I know my nitrogen is sitting up like this or like this? How do I know that? There is a vibrational spectroscopy. This is called electron energy loss spectroscopy. Don't worry, it is a vibrational spectroscopy. It can actually catch the species which are vibrating, which are dancing on the surface. The molecule which are sitting on the surface, they start dancing, right? Or they will keep quiet like this. They will start dancing. So this one, there are two species identified here. This molecule is dancing at higher frequency, this molecule is dancing at lower frequency. What could be the reason for that? Yeah, vibration energy is different. Bond order you should check. Higher the bond order, higher the frequency. Lower the bond order, lower the frequency. This is the one, this is alpha nitrogen, which is a NN double bond species. This is NN triple bond species. You can easily catch that now. So these are all modern techniques which which can be used to identify the species on the surface. Okay. So I'll just skip this probably. Yeah. So that's what I said. So this is where this molecule, this is the adsorb, this is a gas phase molecule. It is coming and sitting here, and then it can give you this pi bonded precursor, and then that can give you atomic nitrogen. That atomic nitrogen will give you NH, NH2, NH3 species. Ammonia is formed on the surface. So these are all identified now. Okay, and here these are the orbitals of nitrogen. Orbital contours of nitrogen. Now, if nitrogen molecule is sitting here like this, the pi star orbital is here. This is the pi star orbital of nitrogen, and then from here you can have some charge. This pi orbital will interact with the iron surface, whereas pi star orbitals get back bonding. Metal carbon is back bonding. The same concept here is pumped into this orbital. As a result, this bond order will decrease. Okay, this is the established mechanism now. Why nitrogen dissociates? If you want to break nitrogen, what do you do? What do you do? I want to break nitrogen without all this. I have to heat it at least something like 1600 degrees centigrade. But this is done at 80 Kelvin. This is done at 80 Kelvin. See the power of catalyst. See the power of catalyst. Okay, I will not bother you about this. I think I will skip this. I will stop here or? Okay, all right. So I had something else to tell you. But anyway, what I am saying is, I think I will stop here. 1 second. I want to show them your last one. Where is the last one? I think okay. I am coming here. Yeah. Now you see. So these are basically the ideas that we have. Now you can work on many things there. So many areas. For example, you see here corrosion, dielectric. These are all catalysis related areas. Oxygen evolution, hydrogen evolution reaction, CO2 adsorption, CO2 conversion, and then hydrogen generation, electrocatalysis, N2O2 CO2 reduction, so on and so forth. These are all areas which are currently important and interesting, and many people are working on these areas. So I am sure some of you can pick it up, and then there is a possibility these areas will have opportunities for jobs in future also. Industries also are interested in these areas, at least particularly this area is something which is very everybody is working on, and also other one is batteries. These are the areas where a lot of work is going on. Industries are also interested. So some of you can actually work in these areas and then get into the industries or academics. Okay, all the best.